you have two tritium nuclei now, two hydrogen-3 nuclei. They're going to collide, and they're going to fuse. You might expect for the product to be 2 protons and 4 neutrons. Well, actually, something a little different again happens, and you actually get 2 protons and 2 neutrons. And actually, what gets thrown out this time are 2 extra neutrons. Because you started with 6 particles, right? You started with 4 neutrons and 2 protons. The end product is only going to be this 2 neutrons and 2 protons, and it throws away those 2 excess neutrons. And this here is actually helium. This is helium-4. The product is helium-4. And each one of these steps produces a lot of energy, and this just happens over and over again. That's how the sun produces all that energy. The net reaction of this then is actually 4 protons. 4 protons will fuse to become a helium nuclei. Oops. Okay. That is the net reaction. 4 protons fuses to become a helium nuclei plus lots of energy. Now, here's the interesting thing. If 4 protons fuse to become 1 helium, and you look on the periodic table, hydrogen, if it's just a proton, has an atomic mass of, let's see, here's hydrogen, has an atomic mass of 1.008, and you're going to multiply this by 4 because 4 protons fuse, and this goes to a helium nuclei. Helium has an atomic mass of 4.003. Now, there seems to be a discrepancy. 4 times 1.008 does not equal 4.003. This product over here is slightly less in mass. It's not much, but it's still missing the mass. Now, isn't matter and energy supposed to be conserved? What happened to that matter? Did we lose matter? Actually, Albert Einstein explains it in his Genius. You may have seen this equation before. E equals mc squared. E equals energy, m is mass, and c is the speed of light. C, speed of light, is actually 3 times 10 to the 8 meters per second. That's a huge number. That's 3 followed by 8 zeros. And if you square the speed of light, 3 times 10 to the 8th squared, that's an even huger number. Ridiculously huge. Ridiculously huge. Okay, that's a huge number. So, what happened to all of that mass, or that small amount of mass that we lost? Well, even if you put that slightly less mass that we have over here, where did it go? Even if you have a tiny amount of mass here, where m goes, you multiply that by the speed of light squared. That's a huge number. And what this equation tells us is that matter that is missing, called the mass defect, that matter that we're missing has been converted into pure energy. It's been converted into pure energy. And that's basically what's happening at all these steps up here. Each time they fuse, energy is being produced. And that energy is actually coming from the fact that a tiny amount of mass, a tiny amount of matter, is actually being converted into pure energy. Again, multiplying that tiny amount of matter by the speed of light is a huge amount of energy. So if we can get fusion power to work by practical means, making a fusion power plant, something along the lines of about 1 gram of protons, 1 gram of hydrogen will be able to power an average American household for about 5 to 8 years or something. And we have plenty of, not necessarily hydrogen, but what we're trying to do here on Earth is we're trying to fuse deuterium. We're starting with deuterium and fusing that, and we can get loads of deuterium from water. It naturally occurs in the naturally occurring isotope in water, and we have plenty of water to extract deuterium from. So if we can do that, all our energy needs would be solved, but the only problem is it's difficult to reproduce the conditions in the sun to make sustainable fusion power. And right now, we are spending more energy inducing and trying to sustain the fusion than what we're getting out. So we're not there yet, but it would be nice if we could get there someday. But yeah, that is nuclear fusion for you. Hope you enjoyed it. The end.